Hi gentlemen, so I hope you are all coping during this lockdown period, and I hope it isn't too tough on you all. I wanted to revise a little bit of electric circuits, and I thought it would be a good idea to do that using what I think a good exercise from your textbooks. So this exercise can be found on page 119. It's Think Tank 10.1 in your grade 11 textbooks. And this exercise focuses on this diagram over here. And let's get started. First of all, we just need to identify what we have in this diagram. We've got, of course, a power source. We have resistors in series and in parallel. And we have voltmeters here, here, and here, and some ammeters. So it's important that we understand what is going on in an electric circuit before we actually try to answer some questions. So it's a good idea to study your diagram before you get started. What I want to first focus on is our power source over here. And there's a whole lot of information in this diagram that is useful to us. It tells us that the EMF is 9 volts. Okay. EMF is the reading of the potential difference of the circuit based on the power source. So it's the total voltage of the power source. And this will be particularly important when we start doing internal resistance. This circuit doesn't have internal resistance yet. So last year, a lot of the work that you did in electric circuits had circuits that either had series connections or parallel connections. The higher level questions consisted of a combination of both. This year you will be expected to know how to work with electric circuits that have a combination of both most of the time. So let's get started with the questions, and then I'll explain a couple of things as we go along. Question 1.1 over here. When switch S is open, what is the reading on V1? What does it mean when a switch is open? I think the answer is quite obvious, that the circuit is broken. That means that we don't have a current flowing. So when there's no current flowing, that obviously affects our readings on the different meters. So first of all, what is current? Current is the rate of flow of charge. And what is charge? Charge is basically electrons that are moving. Remember, electrons have their own charge. It doesn't really matter the size of an electron's charge right now, but what is important here is that the flow of charge causes current and the rate thereof. And current is measured in amps. So the first question is based on voltmeter V1. Voltmeter V1 is connected in parallel, as voltmeters always have to be, and it's connected across the power source, across the battery. Okay? But if this switch is open, even though there is no current flowing, there will be a reading here. And this reading will be the EMF. When we start working with internal resistance, that will be very important, because an open switch will give us the EMF. When the switch is closed, with questions involving internal resistance, then this reading over here is going to change because of the internal resistance. But we're not going to focus on that right now. So, first question is pretty simple. The reading on V1 will be 9 volts. Question 1.2, the reading on V3. Because there is no current flowing, there will be no reading here. Remember, a voltmeter measures the potential difference between 2 points. Here, that reading cannot take place without the flow of current. Here, it still can take place because of the power source being there. Right. So moving on to our next question. Question 2. When switch S is closed, A2 reads 2 amps. Calculate the reading on V2. So now we have this switch closed and there is a current flowing. And they tell us that the current that is measured in this ammeter is 2 amps. We need to remember that a parallel connection is a current divider. In other words, you won't have the total current flowing through both the resistors, or if there are more resistors, they won't experience the same amount of current. Only if the resistors are the same size will they experience the same current. So current is divided in a parallel connection, and it is done based on ratio. So the higher the resistance, the lower the current. The lower the resistance, the higher the current. So there's an inversely proportional relationship between current and resistance in a parallel connection. So the question is, calculate the reading on V2. That's quite simple. We've got the information of the current, we've got the information of the resistance. So all we need to do is we need to plug it into our formula and get our answer. So question 2.1, there's the answer there. V equals I times R. The current is 2, the resistance is 3. 2 times 3 is 6 volts. Alright. So the next question, let's move on to that. What is the potential difference across the 6 ohm resistor? Now the 6 ohm resistor is over here. Interesting that they give us limited space for that answer. Why do you think that is? Well, because although it is a parallel connection, potential difference is not divided in a parallel connection. Only current is. Potential difference is only divided in a series connection. So the amount of voltage experienced in this parallel connection in total and the amount of voltage experienced here will not be the same because it is divided between the two series connections. This 1 ohm resistor is in series to this parallel connection over there. Alright, so the potential difference across the 6 ohm resistor will be the same as the 3 ohm resistor. So it'll be 6 volts as well. Question 2.2, 6 volts. Moving on to question 2.3. Calculate the current through the 6 ohm resistor. So we've got the resistance, we just worked out the voltage, so that's quite a simple one for question 2.3. Again, you just plug it into your equation. R is equal to V over R. You just manipulate your equation somewhat, and 6 divided by 6 gives you 1 amp. Yeah. So now we've got the current going through both the 3 ohm and the 6 ohm resistor. Moving on to question 2.4. How does the current through the 6 ohm resistor compare with that through the 3 ohm resistor? Well, the current through here is 1 amp, that one is 2 amps, and obviously this is going to be less than that. In fact, it is exactly half. If you look at the ratio here, this resistor is twice as big as that one, so that means this one will have twice as much current. Remember, it's an inversely proportional relationship between current and resistance in a parallel connection. Question 2.5. What is the reading on A1? A1 is over here. A1 would be reading the total current. Now there would be two ways of calculating this. Remember, the total current would have split in this parallel connection. So we could easily just say the current going through the 6 ohm resistor plus the current going through the 3 ohm resistor, add them together and it gives you the total current. That's one way of doing it. The other way of doing it would be to get the total voltage and the total resistance, and then calculate the current. We haven't calculated the total resistance yet, so it would be easier to just say, add those two together. So there we go, 2.5, 1 plus 2 is 3 amps, and that is our total current, our total. Question 2.6, calculate the reading on V3. So V3 is over here. We need to calculate the voltage there. Remember, voltage is divided in a series connection. So the total voltage is divided between this series, the resistor over here, and this parallel connection over here. So we know that for the parallel connection, the voltage going through is 6 volts. So once again, we can just do a simple calculation and say 9 minus 6 leaves us with 3 volts going through there. That's the one way of doing it. The other way would be, we've got the resistance, we've got the total current, we can then use the resistance and the current to calculate the voltage. Both would be equally correct, and that is how we can do that calculation. R times R, 3 times 1, 3 volts. Other one is the one I explained first. Voltmeter on the reading of voltmeter 2 plus the reading of voltmeter 3 gives you the total voltage. 9 minus 6 gives you 3. Okay. Then question 2.7, how does the reading on V1 compare with the readings on V2 and V3? I think I've already explained that you can add these two readings to give you that reading. Then question 2.8, calculate the total resistance of the circuit by adding the resistors. Alright, so just move this up a bit. Adding the resistors, that's not too difficult. Remember, there is a specific way with which we must use to add resistors in parallel, and that is the way we do it over here. 1 over Rp, which represents resistance parallel, equals 1 over R1 plus 1 over R2. Then you get fractions. That's resistor 1, that's resistor 2, 1 over 6 plus 1 over 3. Get a common denominator, you get 3 over 6. But it's important here that you show that you have inverted 1 over Rp to be Rp over 1. And that means you invert that as well, 3 over 6 to 6 over 3, and you get 2 ohm. And then that is the total, that's the resistance in parallel. The total resistance is the resistance in parallel plus the resistance in series, 2 plus 1, which gives you 3 ohm. That's the one way of doing it, by adding the resistors. The other way of doing it would be just taking the total voltage and the total current and substituting it into our equation, 9 divided by 3, and it gives you 3 ohms. As you can see, that gives you the same answer. The questions that follow, question 3 onwards in this think tank, is about a change in the circuit and how that change affects the resistance and the current and the voltage and so on. So you're welcome to give that a crack as well. So I think I'm going to just end my lesson there. My intention with this lesson was really just to discuss a few important concepts when it comes to electric circuits and to highlight them by doing some of these questions. So my suggestion would be that you obviously try to do these questions before looking at this video, which I will be mentioning to you anyway. But yeah, gents, all the best, and we'll be moving on to internal resistance soon. Thanks for listening and watching.